Hello everyone, I'm Tatsumi Oba, Panasonic. Today, I will talk about graph convolutional network with suspicious communication pair estimation for industrial control systems. After here, we call our method simply GCN Scope. And industrial control systems, ICS. As background, let's introduce notorious two malwares, Triton and WannaCry. Triton is a sophisticated malware targeting petrochemical facilities in the Middle East. Although there are no evidence found, attackers intruded IT system in some way and reached to engineering workstation. And then they deployed malware Triton, and Triton started to configure SIS controllers. SIS controllers are systems designed for securing processes. However, the attack failed because of deficiency of attackers. But important things is that Triton may have caused critical damage in ICS-specific assets. The next one is WannaCry. WannaCry is also a famous ransomware. And WannaCry is not targeting ICS, but causing damage to ICS. Because many devices in ICS are not patched, the damage in ICS tended to be larger than ordinary IT systems. The damaged companies are from manufacturing companies, railway companies, to water companies, etc. And there are many cases where the amount of damage reaches millions of dollars. So, to mitigate the threat of cyber attacks, we consider it is effective to install securing devices in industrial facilities and monitor them in security operation centers called SOC. We Panasonic are working to monitor connected cars, smart homes, factories, and smart buildings. We also use AI, machine learning algorithms to find anomaly and analyze them. Although there are many ways to monitor ICS facilities, such as factories and buildings, allow listing is considered a suitable algorithm for ICS. And actually, many IDS for ICS use allow listing. So why allow listing is considered effective in ICS? Before talking about that, we explain how allow lists are generated. The allow listing here uses a pair of IP addresses and ports. By using this information, we can detect unexpected protocol not used between two devices. From here, we refer to the communication of specific two devices with specific destination port as link. In the left figure, there are two links in these two devices, a link of HTTP and a link of Modbus. This allow listing can be executed network-based, and network-based monitoring is preferred in ICS. Because network-based monitoring does not interfere with normal operation in ICS, but host-based monitoring needs some installation of softwares and may cause negative impact on operations. However, a serious problem occurs when we use allow listing. the problem of many false alerts. As you can see the right figure, in reality, there emerges many unobserved links in detection phase. In theory, allow listing can memorize all possible communication if running sufficiently long time, but this is difficult for some reasons. One of the reasons is that we would like to change the detection mode to we'd like to change the mode from running mode to detection mode early. We cannot wait for 1 month or 2 months or more to run allow listing. There are also cases where unusual communication such as maintenance, troubleshooting, etc. happen, and these are difficult to observe during running phase. So we propose GCN Scope, which is a method to avoid the problem of many false alerts. Our method enables us to focus only on important alerts and ignore non-important alerts caused by allow listing. We can see the concrete example of the effect of a GCN scope in these figures. Ordinary allow listing causes many alerts like this. The number of out of allow list alerts of a factory of our factories reaches 4,302 only in a week. The number of this is more than 150 times larger than the number of alerts where GCN scope is used in this factory. Furthermore, not only GCN scope reduces the number of false alerts, but it provides us a severity measure of each alert. As you can see, in the case of allow listing, the severity is always constant, which means the communication deviates the allow list run in a week. On the other hand, DCN scope shows us how anomalous the detected communication is. This information is helpful for SOC analysts to prioritize alerts to be analyzed. The main challenge here is how we can quantify the abnormality of unobserved links in environments where unobserved links appear even after running for a long time. If we quantify the abnormality of unobserved links, it is easy to judge whether an unobserved link is anomalous or not by simply thresholding abnormality score. To realize quantifying abnormality score, we take an approach to run the relationship of round links. Round links have source device type, destination device type, and protocol type. If an unobserved link has the same type as round link, it can be considered normal. So running the type of devices and protocol implicitly helps us to predict the abnormality score of links. So in the case of this figure, the unobserved link here has the same source type and destination type and protocol type of these links, which are observed already. But this link, this Modbus link, a completely new link, which was not observed in running phase. So we can use this information to score the normality of unobserved links. Here are key ideas of our method. There are two important points to understand the idea. One is that a link between two devices is determined by their device roles. For example, HMIs are likely to communicate using Modbus with PLC, and historians are likely to communicate using SQL with HMIs or PLCs. The other point is a hypothesis that device roles can be recursively estimated from the role of neighboring devices. Graph convolutional networks are designed to propagate latent vector representation to neighboring devices, which is considered suitable for realizing our idea. So GCN Scope is designed to realize those points. Using graph convolutional network enables latent vector representation of each node. The latent vector here can be considered as roles of each devices. The phase of running links in GCN Scope contributes to improve the accuracy of role estimation. Here is the overview of GCN Scope. While our listing always judges unobserved links as anomalous ones, GCN Scope evaluates how anomalous the unobserved link is and score the abnormality. Suppose the left figure shows links which emerged in running phase. In this case, there are 4 links. If 2 red unobserved links are observed in detection phase, GCN Scope scores how anomalous the links are and judge them normal or anomalous according to the scores and predefined threshold values. You can see the difference of RR listing and GCN Scope with this slide. In both of running phase and detection phase of RR listing, the system monitors target ICS network and extracts communication links. In running phase, the system memorizes all the links appearing in running time. And in detection phase, it queries the memory whether links appearing in detection phase are observed in running phase. And if the link turns out not to be in the memory, the system detects the link as an anomalous one. On the other hand, in GCN Scope, additional steps appears in both phases. In running phase, the process of GCN Scope is the same as RR listing up to the point of memorized links. But GCN Scope then runs a model of AI called RGCN. The run model now has a latent vector representation of each devices and protocols. Then in detection phase, only unobserved link in running phase are to be scored using the random model. Finally, if the score of an observed link is smaller than predefined threshold value, the link is considered anomalous. To understand how GCN Scope works, it is convenient to understand RGCN, which is a building component of GCN Scope. RGCN is multi-graph extension of graph convolutional network. As I said, graph convolutional networks are designed to propagate latent vector representations to neighboring devices. As in the upper figure, propagation to node B is executed using the information of neighboring node A and self node B. The latent vector of node B after propagation is obtained according to this equation. In this equation, HA indicates the latent vector of node A. HP indicates the latent vector of node B. And W indicates how to propagate the latent information. Please don't care about CB, function sigma, and L here. What is important here is that the latent vector of node A and node B are propagated to obtain ideal latent vector of node B. In the case of RGCN, the propagation rule is quite similar to ordinary GCN. The difference is that different protocols propagate latent vectors in different ways. As in the lower figure, node B and node A has two links, HTTP link and MSSQL link. The propagation equation shows that the latent vector of A is propagated according to the protocols used between the two devices. So here is propagated information from node A with HTTP protocols, and this is propagated information using MSSQL links. So let's see the running phase of GCN Scope. In step 1, observed links in running phase are converted into a multigraph. A multigraph is a graph which is permitted to have multiple edges, that is, edges that have the same end nodes. In step 2, RGCN extracts vector representation using propagation rule described in the last page. Note that the vector representations of each node here is completely at random before running RGCN. And step 3 is a step to run where links do and do not exist in the multigraph. In the case of this figure, some existing links and not existing links are extracted. In the first case, device A and device B are connected with SMB links. So, as in this figure, the vector A transpose SMB matrix and vector D is run to be high value. And the second case, device B and device C do not have link of SMB. So the value of vector B transpose SMB matrix and vector C is run to be low value. After repeating step 3 again and again, we finally obtain the ideal vector representation of each devices and protocols. The scoring phase of GCN Scope is very simple. In step 1, we simply extract each representation obtained in running phase. In step 2, we extract unobserved links to be scored. In step 3, we calculate the score of target links. In the case of this MSSQL link, we use a latent vector of device A and device C and MSSQL, like this. And we calculate vector A's representations transpose matrix MSSQL, vector C, and if the value is high, we find this link normal, and vice versa. So let's go to the evaluation. This table shows the dataset for evaluation of GCN Scope. We use the data collected in our factories. In each factories, links appeared more than 2,000 in a week. Surprisingly, more than a lot of new links appeared in next 1 week, as you can see from the table as test links. The new links do not include training links and links with new devices or new link types. Here is the experimental results of GCN Scope and baselines. This table shows MRR and hits are 10. Higher is better in both metrics. The intuitive understanding of this meaning of these metrics is how well these methods predict the unobserved normal links. The first baseline is called Dismart, which is a method similar to GCN Scope. Dismart uses latent vector representations but do not execute graph convolution. So Dismart can be interpreted as GCN Scope without graph convolution. The two heuristics used in these experiments are methods which do not use latent vector representations and use information called first-order proximity and second-order proximity of graphs. The last one is informally random scoring. As you can see, GCN Scope outperforms other methods in MRR and hits at 10 in almost every situations. This result means GCN Scope can appropriately score unobserved links. And by comparing GCN Scope with Dismart, it can be seen that the contribution of graph convolution is very large. The comparison of the last slide shows how well these methods predict the unobserved normal links. However, we are curious about the ability to distinguish normal links and anomalous links. In order to test the discrimination performance, we set unobserved random links as anomalous ones and let each algorithm score all the random links and the unobserved normal links. The result is shown in this table. As expected, GCN Scope outperforms all the other methods in ROC-AUC in every factory. ROC-AUC is a metric indicating how well the method quantifies abnormality. And if the method achieves perfect distinction, the value of ROC-AUC equals 1. GCN Scope achieves average ROC-AUC of over 0.95, which is quite accurate. Here is a concrete example of the number of false alerts. The table can be obtained by fixing one threshold value. As you can see from this table, Whitelisting produces hundreds of alerts in 1 week, which seems impractical to use in SOC. However, GCN Scope reduces significant number of false alerts, while keeping random link detection rate about 80%. So GCN Scope makes it possible for SOC analysts to work efficiently. The performance setting of GCN Scope is quite easy. Although GCN Scope can run links unsupervised manner, ROC curves can be obtained using random links. If you value the number of false positive, you can set the slider handle to this position. In this case, GCN Scope achieves 80.5% detection rate and 2.0% false positive rate. And if you vary the number of detection rate, you can set the slider handle to this position. In this case, DCN Scope achieves 98% detection rate and 20.3% false positive rate. Maybe some of you care about the computational cost of RGCN Scope, but please don't worry. This is a computational time using my laptop. the time of running links in 1 week took several minutes. But this does not matter because it is enough to run the model once in a day or a week. The notable point is the time of scoring. It only takes several milliseconds per unobserved link. This means we can ignore the computational cost of the scoring and makes GCN Scope to be deployed easily. So here's a takeaway. So thank you for listening to my presentation.